Mastering the Data Challenge in Atomistic Machine Learning. Unlocking the potential of atomistic machine learning, a data-driven journey. In the rapidly evolving landscape of molecular and materials research, machine learning models are emerging as powerful tools, revolutionizing the way we understand and manipulate the fundamental building blocks of our world. However, as these models become increasingly mainstream, a new challenge has arisen: the urgent need to improve the nature, quality, and accessibility of atomistic data. Chiheb Ben Mahmood, John L. A. Gardner, and Volker L. Deringer, esteemed researchers in the field of computational science, have shed light on this crucial issue in their insightful commentary published in Nature Computational Science. They emphasize that the next frontier in atomistic machine learning lies not only in the development of increasingly sophisticated algorithms, but also in the curation and stewardship of the very data that fuels these models. The researchers argue that the success of machine learning-driven discoveries hinges on the availability of high-quality, diverse, and well-curated datasets. These datasets must capture the intricate nuances of atomic-scale phenomena, spanning the vast expanse of molecular and materials science. Only then can we unleash the true potential of these computational tools, unlocking new avenues for innovation and discovery. Interestingly, the authors highlight the untapped opportunities presented by a new generation of generally applicable datasets and distillable models. These versatile resources could transcend the boundaries of traditional research silos, fostering cross-pollination of ideas and enabling researchers from diverse backgrounds to collaborate and push the boundaries of what's possible. One particularly intriguing aspect of the commentary is the emphasis on the need for robust data governance and accessibility. The researchers underscore the importance of making atomistic data readily available, not only to established research groups but also to emerging scientists and curious minds. This democratization of knowledge, they argue, could catalyze a surge of creativity and drive transformative breakthroughs. As the authors delve into the technical nuances of data management, they also touch on the ethical considerations that must be woven into the fabric of this data-driven revolution. Ensuring privacy, security, and responsible use of atomistic data will be crucial in building trust and fostering a sustainable ecosystem of innovation. The commentary by Ben Mahmood, Gardner, and Deringer serves as a clarion call for the scientific community to unite and address the data challenge in atomistic machine learning. By embracing this opportunity, researchers can unlock new frontiers of understanding, paving the way for a future where the building blocks of our world are manipulated with unparalleled precision and efficiency. Source: www.nature.com. Unlocking the potential of biomarkers in immunotherapy for solid tumors. Here is my story summarizing the key information from the provided text, a sweeping saga of science's quest to predict immunotherapy response. In the thrilling arena of cancer immunotherapy, where cutting-edge treatments harness the power of the immune system, researchers have embarked on a relentless quest to uncover predictive biomarkers that can guide patient selection and maximize therapeutic impact. Over a decade has passed since the revolutionary approval of immune checkpoint inhibitors, ICIs, for treating a range of solid tumors, yet the challenge remains: many patients still display limited response. While FDA-approved biomarkers like PD-L1 expression, microsatellite instability, and tumor mutational burden offer valuable insights, their utility is often hindered by inconsistent performance across cancer types. Undeterred, scientists have delved deeper, exploring a tapestry of novel tissue-based biomarkers that paint a more comprehensive picture of the tumor-immune interplay. Intricate gene signatures, antigen presentation profiles, and detailed maps of the tumor microenvironment have emerged as promising predictors. But the complexity of these biological systems has proven daunting, with tumor heterogeneity and patient variability posing significant hurdles. Embracing the dynamic nature of the immune response, researchers have turned to innovative longitudinal approaches. Liquid biopsies monitoring circulating tumor DNA and immune cell profiles offer a window into real-time changes, while cutting-edge radiomics models harness the power of medical imaging to track treatment-induced alterations. Even the gut microbiome has emerged as a surprising player, with distinct microbial compositions linked to ICI outcomes. The ultimate holy grail, however, lies in the realm of personalized medicine. Neoadjuvant trials and patient-derived tumor models are paving the way for tailored treatment selection, allowing clinicians to assess individual response before committing to therapy. As these novel strategies gain momentum, the promise of precision oncology shines ever brighter. Underpinning this quest is a global collaborative effort, with pioneering consortia like the PACT, HTAN, and CMAX-CIDC networks driving the field forward. By pooling resources and expertise, these initiatives are poised to unlock the next generation of predictive biomarkers, ushering in a new era of personalized cancer immunotherapy. Source: www.nature.com. Navigating the changing landscape of artificial intelligence. Navigating the AI revolution, safeguarding scientific integrity in the digital age. In the rapidly evolving world of science, researchers are confronted with a transformative new tool, artificial intelligence, AI. This powerful technology, particularly generative AI models like ChatGPT, holds immense potential to revolutionize how scientists conduct research, communicate their findings, and streamline the publishing process. Yet, as with any revolutionary advancement, this AI revolution presents a minefield of legal, ethical, and practical challenges that must be carefully navigated. As a leading scientific publication, Nature Geoscience is at the forefront of this technological shift, recognizing the need to protect the transparency and integrity of the research it publishes. The journal has established a set of ground rules to govern the responsible use of AI, ensuring that the scientific community can harness its benefits while mitigating the inherent risks. Firstly, Nature Geoscience has made the bold decision to prohibit large language models, LLMs, from being credited as authors on research papers. While these AI tools can assist in text generation, they cannot satisfy the criteria for authorship, which requires personal accountability and approval of the manuscript. Instead, the journal mandates that any use of LLMs must be transparently disclosed in the paper's methods or acknowledgement section. Secondly, the publication has taken a firm stance against the use of AI-generated images and videos, at least for the time being. The legal and research integrity issues surrounding the provenance and accuracy of such content remain unresolved, posing a threat to the credibility of the published work. However, the journal does permit the use of non-generative machine learning tools to manipulate existing images, provided this is clearly disclosed. The challenges extend beyond just the author's contributions, as Nature Geoscience has also established guidelines for the use of AI by peer reviewers. While the temptation to utilize LLMs to summarize or assist in writing peer review reports may be strong, the journal recognizes the importance of maintaining the technical expertise and accountability of the review process. Reviewers are asked to refrain from uploading manuscripts into generative AI tools, and any other AI-assisted evaluations must be transparently declared. As the scientific community navigates this new frontier, a common-sense roadmap of best practices is emerging. The overarching principle is that human oversight and critical thinking are essential to preserving the integrity and transparency of research. Authors must not blindly adopt the output of LLMs, but rather think critically about the accuracy and appropriateness of the generated content. The journal's policies also acknowledge the potential benefits of AI for authors who face language barriers in communicating their research in English. While LLMs may be enticing, the journal encourages authors to consider alternative solutions, such as seeking editing assistance from colleagues, recognizing that clear communication, not perfect grammar, is the priority. As the AI revolution continues to unfold, Nature Geoscience is committed to regularly reviewing and updating its policies to ensure that the scientific community can harness the power of this transformative technology while upholding the highest standards of research integrity. The road ahead may be uncharted, but with a steady hand and a commitment to ethical practices, the scientific community can navigate this new digital landscape and unlock the full potential of AI in the pursuit of knowledge and discovery. Source: www.nature.com. Revolutionary robotic exoskeleton learns and adapts to users with simulated training. Pushing the boundaries of assistive technology, a robotic exoskeleton that adapts to its wearer. In a groundbreaking development that could revolutionize the way we approach mobility-enhancing devices, a team of researchers has unveiled a robotic exoskeleton that adapts to its wearer through simulated training. This innovative approach, detailed in a recent study published in Nature, promises to unlock a new era of personalized and versatile wearable technology. The key to this breakthrough lies in the researchers' strategy of training the exoskeleton's control system entirely through simulation, without the need for extensive human experimentation. By combining a detailed musculoskeletal model of the human body with a physics-based model of the exoskeleton, the team was able to create a virtual environment where the device could learn to seamlessly integrate with its wearer. Using reinforcement learning, a powerful machine learning technique, the researchers conducted millions of simulated scenarios, allowing the exoskeleton's control algorithms to optimize their performance and adapt to a wide range of movements, from walking and running to stair climbing. This simulation-based approach not only streamlines the development process, but also enables the device to transition smoothly between different tasks, a major challenge that has plagued traditional exoskeleton designs. The beauty of this approach is that it takes the user out of the equation, explains Alexandra S. Voloshina, the lead author of the study. By training the exoskeleton in simulation, we can develop a controller that is adaptable and responsive to the individual, without the need for extensive user-specific tuning or training. Indeed, the researchers' custom-built hip exoskeleton demonstrated impressive results when tested in the real world. By relying on basic kinematic measurements, such as the angle and angular velocity of the wearer's thigh, the trained controller was able to provide assistive torques and seamless transitions between walking, running, and stair climbing, significantly reducing the energy expenditure of the users. This breakthrough holds immense promise for individuals with motor disabilities or those seeking to enhance their physical capabilities. By eliminating the need for arduous user training and personalized tuning, the simulation-based approach paves the way for more accessible and user-friendly wearable assistive devices. Moreover, the researchers believe that their framework can be expanded to address a wider range of movements and user preferences, beyond the cyclical tasks explored in this study. We're excited to explore how this simulation-based strategy can be applied to more discrete and complex movements, says Voloshina. The goal is to create exoskeletons that can truly integrate into the user's daily life, providing natural and intuitive assistance. As the field of wearable robotics continues to evolve, the work of Luo and colleagues serves as a shining example of how innovative thinking and advanced simulation techniques can push the boundaries of what's possible. With this new class of adaptable exoskeletons, the future of mobility-enhancing technology is poised to take a giant leap forward. Source: www.nature.com. Unlocking the impact of gene regulation on health and aging. Here is a compelling and engaging story summarizing the text on gene regulatory networks in disease and aging, unraveling the genetic tapestry of aging and disease. In the intricate dance of life, gene expression is the conductor, orchestrating the symphony of cellular function. But as we age, this delicate balance begins to falter, contributing to the onset of debilitating diseases. Scientists have uncovered a powerful tool to decipher this genetic choreography: gene regulatory networks. These computational models map the complex web of molecular interactions that govern gene expression, providing invaluable insights into the mechanics of aging and disease. By integrating diverse OMICS data, researchers can now identify the key regulatory hubs and pathways that underlie cellular dysfunction. Take the case of the transcription factor WT1, a critical regulator of kidney health. As we grow older, WT1 levels decline, disrupting the expression of its target genes and contributing to the degeneration of podocytes, the filtering units of the kidney. But researchers have found that senolytics, drugs that eliminate senescent cells, can partially restore WT1 activity, offering a potential avenue for therapeutic intervention. Beyond individual genes, gene regulatory networks can reveal the broader coordinated changes in gene expression that accompany aging. Studies have shown a consistent age-related decline in the global coordination of gene expression, suggesting a widespread breakdown in the regulatory mechanisms that maintain cellular homeostasis. This loss of gene expression control may underpin the multifaceted phenotypes of aging, from impaired protein homeostasis to mitochondrial dysfunction. The power of gene regulatory networks extends beyond aging, providing a lens into the molecular drivers of diverse diseases. In cancer, for example, mutations can restructure signal transduction networks, hijacking cellular proliferation. In polycystic kidney disease, dysregulation of calcium and CAMP signaling disrupts the balance of cell growth, leading to cyst formation. As single-cell and spatial technologies push the boundaries of molecular profiling, gene regulatory networks are poised to become essential tools for deciphering the cellular narratives underlying health and disease. By unraveling the intricate tapestry of gene expression control, researchers can unlock new strategies to restore cellular harmony and combat the ravages of time. Source: www.nature.com. Building optical microresonators, innovations in supramolecular assembly of organic materials. Unlocking the Secrets of Organic Microresonators, a Breakthrough in Optical Sensing and Beyond. Source: www.nature.com. In a remarkable feat of scientific ingenuity, a team of researchers has pioneered a groundbreaking approach to the assembly of optical microresonators using functional organic materials. These microscopic marvels, capable of confining light within their structures through total internal reflection, are poised to revolutionize fields ranging from chemistry and biology to sensing and optoelectronics. The key to their success lies in the versatility of supramolecular chemistry. By harnessing the self-assembly properties of organic molecules and polymers, the researchers have been able to create spherical particles with diameters ranging from just a few to tens of micrometers. These particles exhibit a striking degree of symmetry and smoothness, characteristics essential for efficient optical resonance. Unlike traditional inorganic materials, which require complex fabrication techniques like photolithography, the organic microresonators can be produced through simple solution-based methods. This accessibility opens the door to a wide array of functional materials, including those designed for chemical and biological applications. The real magic, however, lies in the interplay between the optical properties of these microresonators and their chemical or biological functions. By incorporating responsive moieties, the researchers have created sensors capable of detecting minute changes in their environment, such as the presence of volatile organic compounds or fluctuations in humidity. The sensitivity of these sensors is truly remarkable, with the ability to detect concentrations as low as parts per billion. But the versatility of these organic microresonators extends even further. The researchers have demonstrated their ability to act as flow meters, tracking the movement of air currents with exquisite precision. They have also leveraged the resonator's responsiveness to deformation, creating liquid-based optical devices that can sense changes in fluid flow. Perhaps the most intriguing application lies in the realm of biology, where the organic microresonators have shown promise as in situ probes for monitoring enzymatic reactions. By embedding the resonators within biological samples, the researchers can track the kinetics of these processes with unparalleled detail, opening up new avenues for understanding the complex workings of living systems. As the field of organic microresonators continues to evolve, the possibilities are truly boundless. From environmental monitoring to biomedical diagnostics, these innovative devices are poised to redefine the way we interact with the world around us. The future is bright, and the future is organic. Source: www.nature.com. Capturing ultra-fast electron bunches in action. Capturing the unseen, unraveling the secrets of ultra-short electron bunches. In the captivating realm of laser plasma accelerators, where electrons are propelled to dizzying speeds in mere millimeters, a team of intrepid scientists has achieved a remarkable feat. Researchers from the Kansai Institute for Photon Science, Osaka University, and RIKEN in Japan have developed a pioneering technique that allows them to capture the three-dimensional structure of these ultra-short electron bunches with unprecedented precision. Laser plasma accelerators, driven by high-power lasers, can generate electron bunches with durations of just a few femtoseconds and currents reaching into the kiloampere range, a remarkable accomplishment that rivals the performance of conventional accelerators. However, fully understanding and harnessing the potential of these cutting-edge devices requires a deep understanding of the spatio-temporal structure of the accelerated electrons. Enter the innovative approach devised by Kai Huang and his colleagues. By combining the power of optical transition radiation, OTR, imaging and electro-optic, O, sampling, they have managed to reconstruct the three-dimensional density distribution of these elusive electron bunches with astonishing resolution. The OTR imaging provides insights into the transverse profile, while the O sampling unlocks the temporal structure, allowing the researchers to paint a comprehensive picture of the electron bunch's dynamics. The key to their success lies in the clever integration of these complementary diagnostic techniques. The OTR signal, generated when the electron bunch interacts with a stainless steel foil, is captured by a camera for transverse profiling and a gallium phosphide crystal for O sampling. Within the crystal, the temporal information of the electron bunch is imprinted onto the transverse profile of a probe laser beam, enabling the researchers to decipher the intricate details of the bunch's structure. But the story doesn't end there. Huang and his team didn't simply settle for a qualitative understanding, they pushed the boundaries further by employing a genetic algorithm and a sophisticated numerical model to quantify the 3D structure of the electron bunches. Their analysis revealed that these bunches possess a duration of just a few femtoseconds, a peak current exceeding 1 kA, and a transverse size of less than 30 micrometers, all packed into a mind-boggling peak density of 9 × 10 to the 21 meters (3). This remarkable achievement is more than just a feat of experimental prowess, it's a crucial step towards realizing the full potential of laser plasma accelerators. Applications such as ultrafast electron diffraction and compact X-ray sources demand exceptional beam quality, and the ability to precisely characterize these electron bunches is essential for further advancing the field. Moreover, the approach pioneered by Huang and his colleagues serves as a shining example of the power of cross-disciplinary collaboration and data-driven techniques. By drawing inspiration from concepts in computed tomography and laser diagnostics, they have paved the way for a new era of snapshot imaging that can capture the intricate spatio-temporal structures of intense particle and photon beams. As the race to push the boundaries of laser plasma accelerators continues, the insights gained from this study will undoubtedly fuel further advancements in our understanding and control of these remarkable devices. The future holds exciting possibilities, and the journey to unravel the secrets of the unseen has only just begun. Source: www.nature.com. Analyzing Mandarin speech patterns for monitoring Parkinson's disease progression and brain impairment, unlocking the secrets of Parkinson's speech, innovative acoustic insights from the East. In a groundbreaking study, researchers have uncovered a novel approach to diagnosing and monitoring Parkinson's disease, PD, in Mandarin-speaking individuals. By leveraging the power of cutting-edge acoustic analysis, this study has bridged the gap between the Eastern and Western worlds, shedding light on the unique speech patterns of PD patients across language barriers. The research team, led by a talented team of scientists, meticulously examined a cohort of 160 Mandarin-speaking participants, including 80 PD patients, 40 healthy controls, and 40 MRI controls. Through a comprehensive screening of prosodic, articulatory, and phonatory abnormalities, the researchers were able to differentiate between healthy individuals and PD patients with an impressive area under the curve, AUC, of 0.931. Interestingly, the study revealed that the speech disorder characteristics observed in Chinese-speaking PD patients differ from those seen in non-tonal languages. While features like running standard deviation of fundamental frequency, RSTD, and running variation of amplitude, RVAM, during reading were less sensitive in distinguishing PD from healthy controls, the researchers identified a unique set of acoustic markers, including slow average diadochokinetic rate, DDKAVR, slow net speech rate, NSR, longer duration of pause intervals, DPI, increased standard deviation of F0 in sustained vowel, A, F0 STD, increased regularity of the second formant variations, F2 reg, and reduction in vowel space area, vowel area, that proved highly effective in PD diagnosis. But the study's impact extends beyond just diagnosis. The researchers delved deeper, exploring the relationship between these vocal biomarkers and the underlying brain structures and functional connectivity. Their findings revealed intriguing insights, suggesting that the speech impairment in Mandarin-speaking PD patients encompasses not only motor aspects of speech but also cognitive processes underlying language generation. For instance, the study uncovered a correlation between prolonged pauses and atrophy in the left hippocampus, along with decreased nodal local efficiency and nodal efficiency. This underscores the role of the hippocampus in language processing and the cognitive aspects of speech in Mandarin-speaking PD patients. Furthermore, the researchers observed reduced functional connectivity between the temporal lobe and the striatum, as well as decreased activation in the premotor cortex, suggesting a broad-scale network disruption encompassing both cortical and subcortical regions. These findings hold immense clinical significance, as they pave the way for personalized and objectively monitored interventions for effective management of speech disorders in PD. By identifying the specific brain regions associated with speech impairment, the study lays the groundwork for more precise treatment strategies, ultimately improving the quality of life for Mandarin-speaking PD patients. Importantly, this study extends the conventional speech examination protocols and paradigms, which have been predominantly based on non-tonal languages. By adapting the methodologies to the Mandarin tonal language, the researchers have created an opportunity for the vast language group to share harmonized results, contributing to a deeper understanding of PD and its impact on speech across diverse populations. As the world becomes increasingly interconnected, Studies like this one serve as a shining example of the power of cross-cultural collaboration. By bridging the gap between Eastern and Western perspectives, the researchers have paved the way for a more comprehensive and inclusive approach to understanding and managing Parkinson's disease, a testament to the transformative potential of scientific inquiry. Source: www.nature.com